Okay, in the last class, we discussed about the formats of the instruction, particularly the R format instruction, and the instructions related to the load and store instructions. It is how data memory operates or functions. We shall see in detail the instructions, how load and store instructions are executed, but we discussed that the address for the data memory is calculated by CPU. Then let us see little about the branch instructions, and again later on we shall see the details of the branch instruction, how they are executed. Branch instructions are the instructions in which the normal flow of execution is varied or it is changed. Either certain number of instructions are skipped, or the execution need to go back certain number of instructions. Okay, so normally contents of PC are incremented by 4, but in case of branch instruction, the contents of PC, they are incremented or decremented by multiple of 4, and that depends on how many instructions to go back or how many instructions to skip. So that depends on that branching instruction. So in the branching instruction, registers are required to be read, okay, because the branch instruction may be conditional branch instruction, and after comparison of some operands which are stored in the register, the branch will take place or it may not take place. Okay, so depending on the result of the comparison, the branch will take place or not, it will not take place. Okay, so in case of such conditional branching instruction, ALU will be used to compare the operands. Okay, so arithmetic and logic unit, what it does is that it subtracts the two operands which are there in the two different registers, and after subtraction, it checks the whether the output is 0 or not. If the output is 0, then the branch will take place, and appropriate control signal will be given. So calculating the target address is done in this fashion. The sign extension displacement is specified in the instruction. So shift left operation occurs on that particular displacement which is there in the instruction. So sign extend displacement is nothing but a signed number. So this particular number specifies how many instructions are to be skipped or how many instructions to go back with respect to the next instruction. How many instructions are to be skipped or how many instructions to go back from the next instruction. If the target address is of the previous instruction, that is, it is to go back, then that number is a negative number. And if it is a certain number of instructions are to be skipped, then it is a positive number. Okay, Now shift left operation is performed. What is the effect of the shift left operation? Shift left operation, if it is performed once, then it is equivalent to multiply by 2. Shift left operation, in case of shift left operation, if you perform shift left operation on a certain number, that is each bit in that particular binary number is shifted left by 1 bit position, then it is equivalent to multiply that number by 2. So if 2 times shift left operation is performed, then that number is multiplied by 4. So if you want to skip 2 instructions, so if this number is plus 2, then uh, the shift left will occur to two times shift left would multiply that plus 2 by 4, so that will be plus 8. So that means the displacement, the word is displacement, will be plus 8, and to the contents of PC, the that is to this will be added to PC plus 4. Okay, so with respect to that particular content, so this particular number will be added to that particular address. That means 8 will be added. We want to skip 2 instructions, so 2 instructions meet 8 locations, so 8 will be added to the current content of PC. Okay, so already the for the contents of PC are incremented by 4 by the first adder, and to that this particular 8 will be added. Okay, so you can see here this particular diagram. Okay, so the instruction contains, or it is the branching, let us say this is the branching instruction. This particular branching instruction will contain the 2 registers. We will specify 2 registers which are required to be compared, based on which the jump is to be taken or it is not to be taken. So the instruction tells which register 1 is to be read and which is the read register 2, so that uh, the the output of the first register will come out at the read data 1, and output of the second register selected by this will come out at read data 2. So ALU will compare these two contents of this 2 register or this particular 2 number. Okay, so basically it will perform the subtract operation and it will check whether the result is 0 or not. So this will be given to the branch control logic. So it will decide whether the branch is to be taken or it is not to be taken. That means whether this particular sum, this particular adder is now going to calculate the target address. So whether this particular address is to be stored in the PC or the address calculated by the previous adder is to be stored into the PC. So one of the operand to this particular adder is already PC plus 4, and the second operand is received from this particular instruction. Okay, so the instruction is there. So the instruction contains that particular 16-bit number. It is sign extended to 32-bit by this particular sign extension unit, so that so when the number is to be converted from 16-bit to 32-bit, then that number is so converted that if the number is positive, it will remain positive. If the number is negative, the number will remain negative, because the MSB of that particular number signifies the sign of that particular number. So if you copy the MSB into the remaining 16-bit which are required to be extended, then the value of that particular number will not change, only the length of that number will change. The number, if it is positive, it will remain positive. If the number is negative, it will remain negative. Okay, in case of decimal number, even if we precede that particular number with zeros, the value of that number does not change. Okay, so in case of signed binary number, if you copy the MSB bit which indicate the sign into the bits to be extended, then the value and sign of that number does not change. Okay, so you can verify this operation yourself. So this 16-bit number is converted to 32-bit number, and as discussed, it is shifted by 2 bits so that it is multiplied by 4, and that number will be added to PC plus 4 by this particular adder, and that address will be given to the PC, that is program counter. So like this, the next instruction will be fetched not from the next memory locations, but it will be fetched after skipping certain number of instruction. If this number is positive number which is there in the instruction, or if this number is negative number, in fact you will be subtracting, though it is adder, but if one of the number is negative, then it will be subtracting that number from PC plus 4 address, and in that case the address will be of some previous instruction, and the contents of PC will be pointing to the previous instruction, and that instruction will be fetched. Okay, so this is how is the adder that is used. This is the additional adder that is used in case if it is a branching instruction. Okay, so if it is a branching instruction, then registers take the element that are used to execute this particular instruction are the registers, then the sign extension unit, then this is a 2-bit shift register, you can say, the ALU, and the second adder. Okay, so these are the elements that are used in case of the execution of the branch instruction. Okay, uh, then actually some part is not shown properly, is coming properly in this slide. Okay, so uh, the first cut data path does an instruction in one clock cycle. Okay, so usually one clock cycle is required for each of the operation. So each data path element can only do one function at a time. Okay, so at a time, either the instruction can be fetched, or data can be read from the registers, or operation can be performed in the ALU, or data can be written into the data memory, or data can be read from the data memory, or the results can be stored back into the registers. Okay, so for each of these particular operation, you need one cycle. Okay, so hence we need a separate instruction and data memories. Okay, we use the multiplexer wherever alternate data sources are used for the different instruction. Okay, so the appropriate multiplexers need to be used wherever they are required. Okay, so this is the data path for the R-type load store R-type load and store data path, which is being shown here. Okay, that is, here your instruction comes. In every instruction specifies the address, the registers, addresses of the registers. It may contain 16-bit displacement. 16-bit displacement can be converted to 32-bit displacement by this particular sign extension unit. Okay, then this 32-bit displacement, it can be used by the ALU for the purpose of addition to the contents of this particular other register, which is the adder. Okay, so this is basically done when data is to be read from the data memory or it is to be stored from the data memory. Okay, so when writing the data to the data memory, so in that case, uh, uh, the one of the register contains the address of the memory, but that is not directly the address. It is this sign extension displacement is added to that particular address, and the result address is given to this particular data memory. Okay, then when you are writing data to the memory, then in that case, this particular uh, uh, read data too. So the contents of the second register are read. So they are given to the data memory so that which can be written into the data memory. Okay. The other way is that the data is not to be written. The whatever is calculated by this particular ALU is the result of some operation. Okay, for example, contents of two register are to be added. So in that case, this multiplexer will select the contents of this register. Okay, and the contents of two register, they will be added, and in that case, that addition is not given to this data memory. The data memory does not play any role in that case. Okay, so whatever is the result of this particular ALU, it is given. It is also given to this particular multiplexer, and this particular the control of this particular multiplexer select the output of this particular ALU result. Okay, and in that case, this multiplexer, when it is this output of ALU is selected, then it goes back, and where it goes back to the right register. Okay, that means contents of two registers are read, they are operation is performed on it by ALU, and the result is stored into the third register back from here. Okay, so that happens in the R type of instruction. Okay, in load instruction, the data is transferred from the data memory to the register. So in that case, contents of data memory will come out here. Appropriate memory read will be given to this particular data memory. Address of memory is given by the ALU. Okay, and in that case, this particular multiplexer selects the output of the data memory, and that output of the data memory is stored into the selected register, which is selected by this particular write register. Okay, so that is how the data will be transferred from data memory to the register. So this is called the load type of instruction, whereas the store type of instruction, in case of store type of instruction, the again the address of the data memory is calculated by ALU with this particular register. One of the register contains the base address, and offset is added from the instruction, converted to offset converted from 16-bit to 32-bit. So this multiplexer will select this offset from the instruction, and addition of that is the base address of the or the actual address of the memory operand. Uh, so where the data is to be written. Now contents of the second register will be written to the memory. So in that case, read register 2 will select the register of which the contents are to be written into the memory. So it will come out on this particular read data 2, and it is given, you can say, to the right data input of the data memory, and memory write control signal is given to this particular data memory, and data will be written into this particular memory. Okay, so you can see here that this is the data path. Okay, that is, the data can be stored from register to ALU. Both the contents of two registers can be given to the ALU, or the register, ALU, and the data memory. Okay. Of course, the data path is there for the displacement, which is there inside this particular instruction to this particular 16 to 32 bit sign extension, and appropriately it convert that particular data to 32 bit. Okay. So like that, multiple data path exist. Okay, multiple data path exist in case of this particular processor. This is unlike the von Neumann architecture. In that case, a single data path is there. A single bus is there on which the data is transferred between the elements of the ALU, okay, or the processor. But in case of this particular MIPS processor, multiple data paths are there. So it is possible it is possible that the different units of this particular processor can work simultaneously. Okay, but how they can work simultaneously, that is pipelining that we are yet to see. Okay, so this is how the movement of data inside the processor may happen, and the multiplexers, they play vital role depending on whether it is the R type instruction, load instruction, or the store instruction. Okay, so again, now this is the full data path. Okay, so it is in this case the instruction memory along with the branching is also shown in this particular uh, diagram. Okay, so in case of branching instruction, what happens is that this particular sign extended the output of the sign extension unit is also given to this particular shift left register, and so that will happen only in case of the branch instruction, and this particular adder is going to add the the add with the output of the first adder, and uh, this particular result will be given to the multiplexer, and this multiplexer will select either the output of the first adder or the output of the second adder. It selects the output of the first adder if it is not a branch instruction. It selects the output of the second adder if it is a branch instruction and the condition specified in that particular branch instruction is satisfied. So this particular multiplexer will select appropriate address for to be written to the program counter, and it will be written into the program counter. Okay, so this is the instruction memory, and in the next cycle from that particular location the next instruction will be fetched. Okay, and that we have already seen. After the instruction is fetched, then depending on the type of instruction, the appropriate data path will be used. Okay, so every instruction involves use of registers. Every instruction involves use of register. So in some instructions, only one register may be used. In some register, two registers are used, while in R type instruction, all the three registers are or three registers are used. Okay, some instruction uses data memory, whereas some instruction does not use data memory. Okay, for example, the load instruction and store instructions, they use the data memory, whereas the R type instruction does not use data memory. Even branch instruction does not use data memory. Okay, ALU, again, ALU is used by most of the instruction, so including load, store, R type instructions, and branching instruction. Only in the case if the branch is unconditional branch, then in that case ALU is not used. Otherwise ALU is used by all the instructions. Okay, so this is the complete data path for the MIPS processor. Okay, so you must remember this particular data path. Okay, so which units are there and how is the data path between these particular elements and how instructions are executed. Okay. Now let us go into the details of the operations that are performed by the ALU of the MIPS processor. Okay. So basically these are some of the operations that are performed by ALU. ALU receives 4-bit control lines from the control unit. Okay. The ALU performs or ALU text part in the load store instruction. Okay, so as to calculate the address, so it actually does the work, the function, that is the addition function it does. In case of the branch instruction, in that case the ALU does the function of subtraction, whereas in case of R type of instruction, the function of the ALU depends on the function field, and in that case the function can be either AND if it is AND instruction. So in that case the ALU control, it will be 0000. So these bits will be given to the ALU so that it will perform the AND operation on the operands. In case of OR operation, it will be 0001. In case of add operation, it will be 0010. In case of subtract operation, it will be 0110. And in case of 0111, it is set on less than. Okay, so this is one of the special operation with the ALU, whereas 1100 is the NOR operation that can be performed by the ALU. Okay, so these are the operations that are performed by ALU. So this particular ALU does not support direct multiply and divide operation. So if you want to multiply or divide, in that case you need to use this particular multiple add operation. So the this is the extended table in case of the various instructions. Okay, the opcode or the instructions, it can be LW. LW stands for load word. SW stands for store word. So this is the load word instruction. SW is store word instruction. BEQ is branch if equal. So this is the branch instruction, and R type instruction is either add, subtract, and or set on less than. Okay, so the ALU opcode for each of these particular instructions, they can be 0000. For LW and SW, it is 0000. For branch if equal, it is 01, and for R type instruction, it is 10. So the operation, the actual operation that is performed by the ALU is in case of load word instruction, it is add operation. In case of stored word instruction, it is again add operation. In case of branch if equal, it is subtract operation. Whereas in case of R type instruction, so it is these operations. Okay, so the function part which is there in the instruction, in the format of the instruction, for these operations it is like this. Okay, so this is encoding of the instruction. The operation is encoded. That means when the control unit finds that it is 100000, then it comes to know that the add operation is to be performed, and it will send 0010 to the ALU so that add operation is performed on the operand. If the function bits in the instruction, they are 0010, then subtract operation will be performed, and to the ALU this 0110 is sent. Okay, so inside the control unit there is a instruction decoder, you can say, and that instruction decoder will decode these particular bits, and depending on that particular decoding, it will generate the appropriate control signal for the ALU. Okay, and it will also generate the appropriate control signals for the other elements, multiplexers and registers and data memory, so that uh, the appropriately that particular instruction is executed. Okay. Now this is at the glance the format of the all the types of major all types of instructions of the MIPS. In the beginning, we discussed about the R type of instructions. So R type of instruction consists of in the R type of instruction, 3 registers are specified. So some operation with the function some operation is specified. So that operation may be add operation, subtract operation, AND operation, OR operation, or NOR operation, and like that. Okay. So the operation will be performed on 2 register RS and RT, and the result is stored in the RD register. RS is the source register, RT is target register. So though it is the name is target, but in case of R type of instruction, RS and RT both are the operands, input operands, whereas RD is the output operand. That means in the third register the result is stored. Okay. The space for each of this particular RS, RT, and RD is 5 bits. That means they specify one of the 32 registers. Then in case of load or store instruction, only 2 registers are specified. Only 2 registers are specified, that is RS and RT. Okay. Whereas in this case, the address is specified, which is called as the which is called the offset. This particular address, 16-bit address, is called offset, and this particular offset is added to the base address. Okay, so base address is contained by register, and base address is contained in case of load and store instruction. Base address is contained by this RS register. Okay. These bits 31 to 26, they are 35, okay, in hexadecimal, or 43, depending on whether it is a load instruction or store instruction. For load instruction, it is 35. These bits are 35, whereas for the store instruction, these bits are 43. Okay, so that number is stored using this. Okay, whereas in case of R type instruction, all these bits, they are 0. Okay, in case of branch instruction, these bits are 4. Okay, that means so of the number 4 is encoded here. Okay, so this determines whether the instruction, this bit number 26 to 31, they determine whether the instruction is branch instruction or a load store instruction, or it is R type of instruction. Okay, now in case of load store instruction, base address is always contained by RS. Okay, whereas the RT instruction, because it is the write, so RT is the instruction, is the register into which the data will be loaded from the data memory. So that is the load operation. But in case of store operation, data is stored into the data memory and from the register. So the RT stands for the source register, of which the data will be transferred to the data memory. Okay, so RT is either the data is loaded into RT in case of load register, and data will be stored into the data memory from this RT register. Okay, so that is in case of the load or store instruction. Okay, and always the operation is with the data memory. So in case of the store and load and store instruction, the transfer is from RT to data memory or data memory to RT register. Okay, the address of the data memory is specified combinedly by the RS register, which is 32-bit, and this particular address. So this particular address is 16-bit address. So 16-bit address is added to the base register, and that is the address of the data memory. So this is how is the store instruction, load or store instruction. Whereas the branch instruction for the MIPS processor contains or it makes use of two register RS and RT. So the instruction is branch if equal instruction. So if these two register contents of these two registers are equal, then this is the 16-bit number which is having sign, and that particular number is converted to 32-bit, and it is shifted left by 2 bits, and that number is added by the second adder uh, uh, to the addition to the result of the first adder, and then that uh, address is stored back to the program counter. Okay, so this is how is the branch instruction. Okay, so major three different types of instructions are there with the MIPS processor. Okay, uh, so uh, we shall stop here now. In the next class, we shall discuss with the data path with the controls, and then later on, we shall move with the advanced operations with this particular MIPS processor. Okay, so if you have any doubts so far on the instructions, okay, so three different types of instructions we have seen: load, store, branch, and R type. So if you have any doubts on this, you can ask your doubt. Yes, any problem with what is discussed in the today's class? I have shared with you the book by Patterson, and what we are discussing is from the chapter number 4 of that particular book. Yes, Sonali, you have any doubt?
Sir, voice is not clearly audible.
Uh, it is not audible right now. It is not audible, or
Voice is
for
breaking, sir.
long back. So for rest of
Voice break.
the uh, okay, today I am conducting the class from college, and I am using my mobile hotspot. So that may be the reason. Uh, I will upload the recording of this lecture, and let us hope that in the recording the voice is all right. Are you getting my? Is it clear now?
Not clearly, sir.
Not yet clear, but let me try from my mobile device. Also, check my. Is it clear now? Check my voice. Hello, students. Is it clear?
Somehow clear, sir.
For rest of the lecture, the voice was not clear. For rest of the lecture, whether I am not clear. Okay. Okay, Aniket is saying that it is good for him. So it may be the local problem even. Okay, we can check the recording, voice recording. If it is clear, then you can replay this. I will see that immediately by for some time the recording will be available to you. Okay. So we shall stop here. I hope all of you have marked your attendance. We shall continue in the next class. All of you may leave this session. After all of you leave the session, then only the recording will stop. We shall continue with the practicals at one batch is supposed to be there. They should join in time.